So, Steve, please.
Yes. Okay, I'm going to see if I can record it as well. Okay. So, excellent. Okay, so thank you very much for the invitation. And so what I want to do today is talk about some work that I began when I was, I guess, a young postdoc, and Alex Kontorovich was a graduate student. And then we've extended this over the years numerous times with, lots of my students. And so I want to talk a little bit about some of the applications of the subject, some of the types of problems one can look at, and some of the things that I hope my students will be pursuing this summer and maybe talking at Cant 2023. Okay, so just a couple of references at the slides in case anybody's interested in more on the subject. And so the motivating question is, if we have a nice data set, we could ask how often are the first digits going to be a 1, how often a 2, how often a 3, and so on. And so the natural guess is about 10% of the time you might start off with the first digit of 1. Then you quickly realize it can't be 10% because we're not going to have 0 as the leading digit. So we change it to 11%. But actually, in many situations, it's about 30% of the time that you have a first digit of 1, down to about 4.6% of the time having a first digit of 9. Interestingly, the first place I ever saw this was in CS course in arithmetic, although I did not realize I was seeing it there because it's just a remark about the analytic versus the natural density of primes, and what fraction of the time does a prime start with the first digit of 1. And if you do natural density, the answer doesn't exist, but if you do analytic density, you actually do get these probabilities. So this was now known as Benford's law, and it occurs in a huge variety of phenomena. So if you look at Fibonacci numbers, this is one of the best data sets you can see for this bias, and we'll talk a little bit about that later. Twitter uses by the number of followers. I don't know if this is real followers or bot followers. That's, I think, under discussion right now. Most common iPhone passcodes, I would prefer not to explain how I have those. Distances from stars to the Earth, that's actually very non-controversial data. So that one I am happy to talk about. All right. So today I want to basically explain Benford's law, give some examples, sketch the proof, and describe some open problems that my students will be looking at. And then it's important to note that a test that indicates fraud might have happened is not proof that fraud happened. There can be unlikely events and alternative reasons. So this is one of my favorite comic strips from Scott Adams. He kindly gave me permission to use this. Your travel expenses are rejected because all of your meal costs are round numbers. You're a liar or worse. I decide what to order based on what totals to a round number after 15% tip. That's worse.
Steve, you disappeared.
This is good. It gives me time to understand the joke.
I gather I'm not the only one that's not hearing anything.
Yeah, Steve, you disappeared, or your voice disappeared. No, I don't know where he is.
Mel, can you hear me?
Now I can. After you put up your cartoon, your voice disappeared.
Can you hear me?
Are you still there, Steve?
Can you hear me, Mel?
Now I can.
Okay, so it was advancing on my computer, but it was not advancing on the Zoom.
Right.
Not just not advancing, we couldn't hear you.
Could you hear any of the talk?
Only up to the cartoon.
Interesting. So as soon as I start talking about fraud, everything crashes. All right. Can you give me permission to share?
Of course. Oh, can't you share as a co-host? But hang on, just to make sure.
It actually kicked me out of the.
There, you can certainly share now. Again.
Okay.
You're coming back on. That's good.
Okay.
That's progress.
All right. Tell me if you can see it now.
Yes, can see it.
Okay. So we saw
Yeah.
this slide.
That's where you stopped before.
Okay. So give me just 1 second. Okay. And then I'm just punching it up on the computer in my classroom for my students to see as well. And then do you have, okay, it's 840 6618 4717. Okay. Okay, so it looks like it's working now.
At least we can see the cartoon again.
Excellent. It's a good cartoon.
It is.
And he was kind enough to allow me to use it. All right. Once more into the breach, dear friends. Okay, so I think I've lost my ability to record this, but I will deal with your recording. Okay. So I was mentioning my proof of the 3x plus 1 problem, but unfortunately, I guess none of you heard that. Okay. So I was just talking about some of the different places where we can see Benford's law. And so we can see it in difference equations, we can see it in differential equations, and this explains why it occurs in so many different areas in science. We can see it in L functions, the 3x plus 1 map. We can see it in lots of different financial settings. Some of the big applications is analyzing round-off errors and optimal ways to store numbers in computer science. And then, huge applications by the IRS and others in terms of detecting text and image fraud, data integrity. This can also be used by security organizations. If you are familiar with steganography, the art of hiding messages and messages, hiding an image in an image, you can actually use Benford's law to determine if an image has been modified, and thus if it's likely that there's a message hidden inside of it. All right, so what I want to do is I want to talk very briefly about the general theory. So for many data sets, the probability of observing a first digit base B is going to be the log base B of D plus 1 over D. So again, base 10, about 30% of the time you'll be a 1. You're going down to about 4.6% of the time. Oops. All right, this seems to be an older version of the slides that I've just loaded, but not a big deal. All right, so just brief notation. Everybody's familiar with modular arithmetic. When we write our numbers, we can write them in scientific notation. So the significand is the number between 1 and the base. So base 10, it's going to be between 1 and 10, and then it'll be times 10 to the k, and that's going to just pad where we put the decimal point. So two numbers have the same significand if and only if they have the same leading digits. And the key observation and the explanation as to why we are able to use Fourier analysis so well is that the log of x base 10 equals the log of x tilde base 10 mod 1 if and only if x and x tilde have the same leading digits. And so if we are studying e to the 2 pi I u, we can replace u with u mod 1 without changing the value. And this is why Fourier analysis is going to be so beautifully set up to handle problems like this. So, since a sequence is equidistributed mod 1, if the probability that it lands in AB converges to the length of the subinterval AB. So, for example, if we take an irrational number, then n beta is equidistributed mod 1. And in fact, a little bit more is true. You can tell how quickly the equidistribution sets in based on the irrationality exponent of beta. And that will be very important later when we look at the 3x plus 1 and Benfordness there. So in particular, if we look at the log of 2 base 10 or the log of the golden mean base 10, we see that both of these are irrational, which is going to lead to powers of 2 and the Fibonacci numbers being Benford. Okay, so because I do not want to risk running a program live, which is probably a good idea given that we've already had one major technology failure already, I just pre-coded one of my favorite irrational numbers, the square root of pi, looked at n root pi mod 1 for the first 10 values, and you can see that this is reasonably close to equidistributed. If every interval of length 0.1 had exactly one number, you would think I'm deliberately choosing a number to make things look good. So the fact that this is a little bit off is good. If we go up to 100, if we go up to 1,000, if we go up to 10,000, you can see the equidistribution setting in very quickly. So the most common way to try to prove that a data set is Benford is to show that its logarithms are equidistributed mod 1. And so, again, if we just write our number as a significant times 10 to the k, all we have to do is understand the log of the significant base 10. I mean, the log of the significant modulo 1. So if we plot the numbers from 1 to 10, and then we plot the logarithms, all the numbers that will have a leading digit of 1, well, when we take the logarithm, that will go from 0 to about 0.3, the log of 2 base 10. And that's why about 30% of the numbers will have a first digit 1. If you're equidistributed on a log scale, then when we exponentiate, your numbers will be Benford when we look at them naturally. So now if we just want to get the probability of a leading digit of d, we would just look at everything up to d plus 1, subtract everything up to d, and that's going to give us the log of d plus 1 over d. So what's really going on with Benford's law is it's looking at things the right way. So I love Rubik's cubes. The one with, I guess, the cross is one of my absolute favorite Rubik's cubes. And when you look at this initially, it looks like a very different cube than the one on the left, the more standard one. But it turns out these cubes are the same if you hold it at a 45-degree angle. And if you look at it the right way, it's the same. So this digit bias in Benford's law, it all evaporates if you just look at the logarithms mod 1, and then it's equidistributed. And in fact, you can look in more general settings. There was a paper a year or so after Benford, which was talking about convergence of measures to the analog of the uniform distribution on various compact spaces. And that's essentially what's going on and giving us the Benfordness. So just to give some specific examples, 2 to the n is Benford, base 10, because the log of 2 base 10 is irrational. So when we look at the log of 2 to the n, we get n log 2. Log of 2 is irrational, so this will become Benford. And we can even say a little bit about how quickly it becomes Benford by knowing things about the irrationality of the log of 2 base 10. If we want to look at the Fibonacci numbers, we start off with the Fibonacci relationship, and very quickly we can get to Binet's formula. And when you look at the second term, because the second factor is less than 1 in absolute value, when we raise it to the nth power, it rapidly tends to 0. So the nth Fibonacci number is essentially 1 over root 5 golden mean to the n. The 1 over root 5 doesn't really matter. And if we just take the log of the golden mean, that's an irrational number, and that's going to give us the Benfordness. Most linear recurrence relations are Benford. And again, because so many things can be modeled by recurrence relations or differential equations, this is some additional evidence in support of the prevalence of Benfordness. So if I give you, for instance, an plus 1 is 2an, this is just going to give us the numbers 2 to the n that we had before, and this will be Benford. But if I give you 2an minus 1, it turns out this will not be Benford. And so this one was deliberately cooked up. If I take a0 equals a1 equals 1, I'll just get every integer in the sequence is 1. If I take a0 equals 0 and a1 equals 1, I just get 0, 1, 2, 3, 4, 5, 6. And so what's going on here is if you look at the characteristic polynomial associated to the recurrence relation, you have a double root of 1. And that's why you're not going to get Benfordness. But for all the others, if you have a if the largest root is such that you're going to be exponentially growing or exponentially, something like that, it's not going to be 1, then as long as this is not a rational root of 10, you will have Benfordness. All right, so looking at the values of 2 to the n to just see how quickly does Benford behavior set in. So this is the first 60 numbers. I'm only displaying the first 30 because the numbers are getting quite large quickly. We can see that for the small numbers, the probabilities look pretty good. They look pretty close to Benford. For the larger ones, especially 9, the probability is not so great. But again, the expected number of events is quite small. A lot of times when you're doing data analysis for something like this, you should probably combine a bunch of things to have a reasonably sized probability and a reasonable number of events. The other thing, though, that's really going on is 2 to the 10 is 1024, which is almost 1,000. So what this means is every time we increase n by 10, we almost return to where we start. We differ by about 2.4%. And that's why if you look at the numbers, so far, every row, each number has the same first digit as the one to the left of it in that row. It's going to be a while before the row with the 8s finally gets large enough to give us a 9. It's going to be a while before we finally get a 7. Okay, choosing just a couple of other numbers to just try to get a sense of how quickly does Benfordness set in, I chose 3 of the most famous irrational numbers: the Euler-Mascheroni constant gamma, the constant e, and the constant pi. And so I calculated the chi-squared value to see how good of a fit is Benford to the data. And I did n goes from 100 to 1,000. And we see that for the first 2, the fit looks very good. If it really is Benford, then we should be getting a value of 15.5 or less. And even for pi, we're still getting good values for Benfordness. It starts off large, gets smaller, but then interestingly, they get larger again. There seems to be some kind of cyclical behavior. And when we looked at powers of 2, what was going on is that we had trouble because 2 to the 10 was 1,024, which was almost 1,000, so it was almost padding by 3 zeros. So plotting pi to the n in red and e to the n in blue, if you look at this, you can hopefully see that the red, the log of the chi-squared seems to be periodic with decreasing amplitude. With period, anybody want to try to guess what the period is? Anybody have really good eyes on Zoom or in the classroom?
Sorry, what is chi?
This is a chi-squared test. I'm just plotting the goodness of fit. And so the larger the chi-squared, the less likely it is that it's given by Benford. And so if your chi-squared value is 15.5 or less, then this is considered a good fit. If it's more than 15.5, it's a bad fit. So even once we get up to 200, even pi is giving us a decent fit with Benfordness, but not nearly as good of a fit as gamma and e. And so just to be able to put everything on the same scale, I'm taking the logarithm of everything. Can anybody guess roughly what the period is of the red pattern? Anybody have really good eyesight?
150?
150. I think it's a little bit more than 150. Let's see, does it zoom in when I do that? Okay. So I think each of the tick marks is 50. And so looking at this, I think it's between the 150 tick mark and the 200 tick mark. Anybody want to refine the guess?
$170.
Yeah, 170. And so most people know pi. A couple of people may know pi squared, but pi to the 175 is 1.0028 approximately times 10 to the 87. So every 175 times we increase, we essentially are just appending 87 zeros. And this is why we see the periodicity when we are looking at things with pi. And so again, the convergence to Benfordness and the fluctuations is greatly tied to the structure of these numbers. So what I want to do is I want to briefly talk a little bit about some explanations for why Benford comes in so many different settings. and then talk a little bit about how we can prove Benfordness in a couple of interesting situations. So the first is, not all data sets satisfy Benford's law. So for example, if you imagine you have a long street where the houses are numbered 1 to L, if L equals 199, you've just gone through a huge number of houses starting with a 1, whereas if it ends at 999, you've just gone through a tremendously long stretch where it doesn't. And so it's going to oscillate between roughly 1/9 of the time and 5/9 of the time, you'll have a first digit of 1. And so instead of plotting the probability versus the street length L, it's actually more natural to plot it against the log of the street length. And you can see, a really nice periodic behavior as you keep lengthening the street. Well, what if we had many streets of different lengths? So there's a lot of papers. Ted Hill has some great papers on the amalgamation of different distributions. And the more amalgamations you have, the more different processes you have going on, the more likely you are to have Benford behavior. So what if we had different streets of different lengths, put in all the houses, and then looked at that distribution? So first of all, I'm going to just take a very simple situation of 1,000 streets, and each street has exactly the same number of houses from 1 to 10,000. And if you look at this, you see, not surprisingly, that the data is not close at all to Benford. It's really nice and uniform in terms of the leading digits. Now what we're going to do is we're going to have 1,000 streets, and each street I'm going to choose its length to be a random number chosen uniformly from 1 to 10,000. And when I do that, it's still not Benford, but it's closer. If I do it one more time, if I choose the street length to be a random number of a random number from 1 to 10,000, this is now pretty close to Benford, both for the first and the pairs of first 2 digits. If I do random, 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 then it's really a good fit. And so this is a general phenomenon that the more mixing you have, the faster Benford sets in. One way to see this is the central limit theorem. So if I have a bunch of independent, identically distributed random variables, then the sum converges to be normally distributed. And if you want, you can subtract off the mean, and you can divide by the standard deviation so it converges to the standard normal. Doesn't really matter. And so just to see how quickly this goes in practice, let's look at sums of uniform random variables. And so if I take just one uniform random variable normalized to have variance 1 and compare that to a Gaussian, it's not great, it's not horrible. But already if I do a sum of 2 uniform variables, it's not that far off from a normal. If I do a sum of 4, it's pretty close. If I do a sum of 8, it's extremely close. You could, of course, explicitly write down, if you want, the densities and work with this, but it is an absolute nightmare to work with expressions like this. And this is why we want to say, it's converging to the normal. Let's just say that the main term is given by a normal, and then control what the error is. So to make these arguments work, no one wants to use densities explicitly like this. We just need some kind of quantified version of the central limit theorem. What's the main term? What's the error in the approximation by the central limit theorem by the normal distribution? So to give a specific example, let's take a normal distribution with mean 0 and variance sigma squared, and let's look at it modulo 1. So we said that a process is Benford if its logarithm is equidistributed mod 1. So let's assume that the logarithm of what we care about is normally distributed. And since we care about what things look like mod 1, we look at the logarithm mod 1. And so here I'm choosing the variance is 0.01. So if the variance is 0.01, that means the standard deviation is 0.1. So that means most of the mass is within plus or minus 0.1 of 0. And if you look at this plot, you can see that most of the mass is within plus or minus 1 of 0, because of course anything near 1, because we're doing things mod 1, that's really the same as being a small negative number just to the left of 0. And so if I have a variance of 0.01, this is very far from being the uniform distribution. So I've got the uniform distribution in some kind of orangey gold. But if I increase the variance to be 0.1, it's not that far off now from uniformly distributed. And again, if our process is such that the log of the process is a Gaussian, if that becomes uniformly distributed mod 1, then we would expect to have, Benford from the original. If we now make the variance 0.5, we see we have a tremendously good fit to a uniform distribution. You always have to look at the scale, and if you look at the y-axis, it goes from, my eyesight is not so good, I think it's 0.9999 to 1.0001. So already with a variance of 0.5, we are extremely close to the logarithm mod 1 being uniformly distributed, which would mean the initial process would be very close to being Benford. Okay, so whenever you see a product, you should always take a logarithm. So imagine we have some process where we have x1, x2, and we care about their product. Well, if we take yi to be the log of xi, and just let vn be the log of the product, then the log of the product is the sum of the logs. And if we're in a situation where the central limit theorem kicks in, we would expect the sum of the logs to become normally distributed, typically with growing variance. And if you have a normal distribution with growing variance, it's not that bad to see that it's going to be converging to the uniform distribution mod 1. And this explains why so many processes become Benford. If we're in a situation where we have a lot of multiplication, a lot of factors like this coming into play, it's going to give us a really nice Benfordness. All right, so I want to turn to a project that I did with the students a couple of years ago, which I think is going to be continued this summer. I had a thesis student working on this past year. I'm going to talk about stick decomposition just in the interest of time, but you could, of course, instead of just splitting a stick by choosing some random variable, you could actually try to talk about splitting a stick into, say, sums of squares, or splitting a stick into primes, and trying to use some number theoretic flavoring for what you want the partitions to be like. So imagine we have a stick of length L, and we uniformly choose one proportion P, and then we will split the stick into two into lengths PL and 1 minus PL. And then each of those sticks will split with the same proportion P, and now we'll have 4 sticks, and so on and so on. So this is the simplest model to do because we're using the same probability every single time. Of course, you could, instead of using a fixed proportion, you could allow yourself to have a different proportion each time and see how that affects things. And so we'll repeat this n times and get n levels and have 2 to the n sticks. And we can ask, what can you say about the distribution of the leading digits of these stick fragments? But again, this is just a more general one. We have the results for 2-dimensional fragmentations, and my interest, of course, would be, if you drop like a giant piece of glass, which they're not willing to let me do here at Williams, and it splits into all these different shards, what can you say maybe about the areas of the pieces or the perimeters of the pieces? There's a lot of natural questions that you can ask. And so here's what it would look like after just 2 levels. Note that we would have one length P, 1 minus PL occurring twice, and then 2 other lengths occurring just once. And so choosing P to be 0.51 and N to be 10,000, if you look at a plot, it looks very close to Benford. The other one is choosing P to be 0.99, again, very close to Benford. So the question is, for which values of P do you expect that you will have Benford in the limit? Well, obviously, if P equals 1/2, it can't be Benford, because then every piece has the same length because P equals 1 minus P. And so very quickly, my students came up with, if you take P equals 1/11, it's not going to be Benford. And there's a natural reason, why you would take P equals 1/11, is rather than writing these stick fragments as, P to the K, 1 minus P to the N minus K, we can just, to the J, we can write it as P to the N, 1 minus P over P to the J. And we can now see that as we go from one length to the next, we just multiply by 1 minus P over P. And so if 1 minus P over P is either a power of 10 or a rational root of 10, then we see that we're going to have something that's cyclic. And every so many iterations, we will just return to where we start. And so again, we can see the algebraic structure of the number, this time 1 minus P over P, is going to come into play and is going to affect whether or not we have Benford and how quickly Benfordness sets in. And so again, if 1 minus P over P is 10 to the Y, if Y is irrational, we can prove that it's Benford. If Y is rational, it's going to be uniform distributed. Okay. And so the proof is actually pretty straightforward. There's a lot of ways you can do this. Let's say 1 minus P over P is 10 to the r over q, then all I really care about is, when I'm looking at my indices, how often do I have various lengths? Every time I increase by q, I'm going to have the same leading digit. And so I'm going to basically just be summing binomial coefficients in arithmetic progression. There are explicit formulas for this, or you can also just say, by just removing a term or adding a term, all of these sums to first order are going to be the same. They're all going to be roughly 1 over q. And that's going to be responsible for a uniform distribution and not a Benford distribution here. Okay, so something discrete. So if p equals 3/11, here's a plot of what's going on. We have something that's irrational. If we take p equals 1/11, you can see a tremendous spike where everything has the same leading digit. Okay. And then for the last part of the talk, I want to talk a little bit about the 3x plus 1 problem and the Riemann zeta function. And so because this is being recorded, I will be very careful what I say in terms of if you want to use this to either detect tax fraud or do tax fraud. I will say detect tax fraud. How can you tell if a data set has been modified? And so a lot of processes are expected to follow Benfordness. And so let me talk a little bit about a general framework that can prove a lot of these processes are Benford. So let's imagine we have some, something x that we care about. We've discussed that we want to look at its logarithm mod 1. That's going to be the easy thing to study. And so if we have some kind of discrete process, we might want to count, how often does n lie in some set A? Maybe A will be the set of numbers, the set of integers leading to a first digit of 1, or maybe it'll be the set of integers leading to, the set of indices leading to a significand that's at most x, something like that. And I want to ask, what fraction of the time does this happen? So, the key ingredient is going to be Poisson summation. So if our function f is nice, the sum of f over the integers is the sum of f hat over the integers. And we'll say that our initial process is Benford good if the following conditions hold. So the first is that we can write the CDF of the logarithm as basically integrating some nice density plus an error term. And we want, the following things to be true. We want small tails so that the probability, if h of t is something going to 0, if the standard deviation is around t, h of t would be a growing number of standard deviations away. We want that to be pretty small. The second one is we want the Fourier transform to have sufficient decay. So we want this sum to be small. And again, in most of the processes, f is going to be the standard normal or some kind of normal distribution. So the decay is not going to be a problem at all. And the last, and this is the most difficult part, it's the small translated errors. That we said that we had a main term for the CDF, which was integrating density plus an error. We need some control over that error. And that is the most difficult part of all the proofs. That's the part where you really have to use things that are specific to the problem that you're looking at. And so, some of the examples where we can apply this are L functions, characteristic polynomials from random matrix theory, 3x plus 1 problem. And so as long as these conditions are satisfied, then the initial process is Benford. And so the proofs basically work as 2 steps. The first part is we use that the main term is something nice that's spreading out, and that's going to become uniformly distributed, and that's going to give us what we want, and then just apply Poisson summation to control the errors. And that's the hardest part, and we'll go through that with 3x plus 1, and if time permits, a little bit with L functions. So just in general, let's say I want to calculate the probability that my y, my logarithm, mod 1, takes on a certain value. Well, if I don't want to do the mod 1, if I just want to, well, I'm sorry, because I want to do the mod 1, I have to look at all the possible values, not just y being between a and b, but between a plus l and b plus l for all choices of l. And so as l varies from minus infinity to infinity, this is going to give me the probability that y mod 1 is in the interval a, b. And so by our assumption, this is just equal to gt at b plus l minus gt of a plus l plus a small error, because we are assuming small tails. We then replace things with our main term plus an error, which we assume can be controlled. And then we use Poisson summation to replace that sum and extend the sum to being over all integers and not just integers less than or equal to th of t. Because of the decay, that's not a problem. And then the main contribution is when L equals 0, and that's just going to give us f hat of 0 times b minus a. And your f hat is going to be 1, so this will just give us b minus a. So this will tell us that y is converging to being uniformly distributed mod 1, which then means that our process is Benford. So if we want to apply this, for example, to the Riemann zeta function, here is a plot of looking at a couple of values, around 65 values of the Riemann zeta function on the critical line 1/2 plus ik over 4. I can't remember if the star or the circle is the Riemann zeta function. I think the circle is Benford and the star is the Riemann zeta function, but the fit is so close it doesn't really make that much of a difference. All right, so let's go through the details about how you would actually deal with these error terms in a specific problem. Let's look at the 3x plus 1 problem. And so there's a tremendous number of great quotes about this. I think my two favorite is Kakatani described this as a Soviet conspiracy to slow down American mathematics, because every time people heard about this, they would say, oh, this can't be so bad, and they would start working on it for a while without any good results, or urged that mathematics is not yet ready for problems like this. So there's a couple of ways we can define it. I'll do the most compact way. If you take an odd number, you multiply by 3, add 1, and then remove as many powers of 2 as you can, all in one step. And we keep iterating. And the conjecture is that no matter what odd integer you start with, eventually you will hit 1. And once you hit 1, you stay at 1 for all time. So for example, if we start at the number 7, 7 would iterate to 11. And I'm going to put a 1 down there because we removed 1 power of 2. It went to 22. 22 divided by 1 is 11. 11 is going to go to 17. Again, we move 1 power of 2. And then just doing a few more, 13, 5, and then 1, removing 2, 3, and 4. So what we can do is we can call an M path will be the sequence of powers of 2 that we remove. So the 2 path for this would just be the first 2 powers of 2 that we remove, which would be 1, 1. The 5 path would be the first ones we remove, 1, 1, 2, 3, 4. And in general, the M path would be the first M powers of 2 that we remove. With a few quick calculations, you can actually look at the expected value of an plus 1, and you'll see that it's equal to where you were before, plus the log of 3/4, which is negative. And since the log of 3/4 is negative, this suggests that as you keep iterating, your number should on average be going down to 1. And you can even use this to estimate how long it would take for you to go down to 1. This suggests that you could have a geometric Brownian motion. Its logarithm is Gaussian with a negative drift. And so back in 2005, Alex and I proved that as m goes to infinity, if you look at the ratio of xm, the mth term from your starting seed, divided by 3/4 to the m x naught, which is where you expect to be, that is Benford. So again, we showed that if you look at where you are divided by where you expect to be, as m goes to infinity, that becomes Benford. And then I gave a talk on this at Michigan, and then Jeff, I'm not sure if he's still here, he and Sound then proved a better version, which basically said that for most of your starting seeds, if you look at your first n iterates, you are within a very small distance from the Benford probabilities. And so the reason we looked at the ratio of where you are to where we expect to be is we actually had really good formulas to predict what was going on and to talk about the structure of these sets. So we have the following structure theorem due to Sinai for 3x plus 1, and then generalized by Alex for more general problems like this, that these ki values are independent, or basically behave like independent, identically distributed geometric random variables. And in this case, with probability 1/2. In particular, if we want to look at the set of numbers who have a given m path to start, it's actually 2 full arithmetic progressions. And so we have a wonderful structure of, if you tell me I want to initially remove 5 powers of 2, then 3, then 7, then 8, then 2, then 1, I know exactly what my numbers like that are going to look like. It's a really nice arithmetic progression. And so because it's converging to a geometric random variable, we can actually calculate, the log of, the probability and compare that to a geometric random variable. And so we can play some games by just rescaling things by putting in logarithms. And so we just want to figure out, what is the probability that this geometric random variable is going to be, less than or equal to a certain number. And now this is going to just become, a nice quantified equidistribution problem. So we first tried to just, argue directly, but the problem is because things were discrete, there were a lot of issues. If we just missed one number every single time, we could have catastrophic reinforcement. And so we really needed a quantified version of equidistribution of how quickly does, if, alpha is irrational, how quickly does n alpha mod 1 become equidistributed? And the speed of equidistribution depends on the algebraic structure of alpha. So we know by the central limit theorem that a geometric random variable Sm minus 2m divided by square root of 2m is going to converge to being normally distributed. So we know we're in a situation where the main term is going to be given by a Gaussian, and then we have some kind of error that we need to control. And the way we control the error is we ask, essentially, how often are various things going to land in different intervals. And this is where, if you know the irrationality type, so we're looking at c equals the log of 2 base b, and we want to know how often is k times c mod 1 in a given interval. If we have m possibilities, if it was equidistributed, the main term is going to be m times b minus a. What's the error? It should hopefully be a smaller power of m. And so you can show for any epsilon, it's m plus epsilon minus 1 over kappa, where kappa is the irrationality type. So what that means is alpha has irrationality type kappa, if that's the supremum of all gamma, where the limit is q goes to infinity of q to the gamma plus 1 times the minimum of alpha minus p over q equals 0. So it's talking about how well can we approximate our number. So algebraic irrationals, they're type 1. And by using the theory of linear forms, we can show the log of 2 base b is a finite type. And so because I was not at all concerned with trying to find the best bound, I just appealed to a theorem of Baker with a bunch of algebraic numbers, heights. And when you go through and put everything in at the end of the day, you get the log of 2 base 10 is a finite type where kappa is at most 1.2 times 10 to the 602. That is a finite number. So if I look at 1 over kappa, it will be a finite number. So as long as I choose epsilon sufficiently small, I will then get that the main term m times b minus a is going to be strictly larger, by a small power of m than the error term. And this will give us, convergence. With a little bit more work, I am sure one could get a much better rate of convergence than appealing to something on the form like 1 over 10 to the 602. And it might be interesting to see, what is the best, convergence rate you could get for some problem like this. It's much better than 10 to the 602. All right, I'm going to skip the rest in terms of how you do it. I'll just, show some of the data. So looking at, 80,000 roughly iterations of, some random number, we can see, terrific fit with Benford. And we're seeing, right now, essentially, 2-3 digits accuracy in terms of the predictions and the results. So, the fit is absolutely wonderful. You could, of course, instead of pulling out all powers of 2 at once, you could say I either multiply by 3 and add 1 as a step, or I pull out a power of 2 as a step. And if you do it that way, it's a little bit more work, but you can also show that you would get Benford as well. You would not surprisingly have a lot more steps. Instead of looking at 3x plus 1, you could look at 5x plus 1. The difference for 5x plus 1, we expect that typically you should explode to infinity. So instead of having the log of 3/4, which is negative, we would expect to have the log of 5/5. We would expect to have a positive drift and explode upwards. And again, absolutely beautiful fit with Benford. All right, so for the last maybe 3 minutes, I just want to briefly say how you would apply this for the Riemann zeta function and show Benfordness there as well. So let me just, okay. So we've had those plots. Okay, so we say an L function is good if it satisfies the following conditions. So the first is, there has to be an Euler product. The second is there's a meromorphic continuation to all of C. Next is there's a functional equation of a certain standard form. So far, these are not big asks for our function. The next one is beginning to get a little bit more. So for some aleph, the sum of AFP squared over P is going to be the form aleph log x. Well, if we take the Riemann zeta function, all of these would be ones we have the sum of 1 over P, and that's just log x. All right, so this is, again, this is not a horrible, ask for something like this. Anything, bounded is going to be fine. The alpha fj's, are of size 1 in absolute value. And then the last one is the number of zeros with real part greater than sigma and imaginary part up to t has the following, bound. So of course, if we assume the generalized Riemann hypothesis, this is not going to be a problem at all. And so this is just, a density conjecture, just, some weak result towards the Riemann hypothesis. And these conditions are known in many settings, for the Riemann zeta function, Hecke-Cuspidal forms of full level and even weight. So there are definitely examples where this holds. And so the key ingredient is the log normal law, which basically says if we look at the log of the absolute value of the L function on the critical line, then the main term is converging to a Gaussian, and we understand what the size is of the variance, and it is growing. And so Alex and I were able to show that for any good L function, this gives us all the conditions we need to go through and then just do the algebra from the Benford good part of the talk and just show that all those conditions are met, and we can control the error terms and everything works out. And so for any L function with these 6 properties, we would have Benfordness. Okay, so I will just briefly conclude that we see many different systems exhibit Benford behavior. And the key ingredients of the proof, it's basically logarithmic transform showing something that then becomes equidistributed. And the difficulty there is you're controlling what the errors are. And for whatever problem you're looking at, you need to develop specific tools for that. A lot of times the algebraic irrationality type of the number becomes extremely useful. It gives us control over how quickly equidistribution sets in. And then there are numerous applications of this to detecting fraud for data integrity. There have been numerous reports over the decades of scientific studies that have been faked. And so the ability to quickly get a sense of whether or not some data is valid is extremely useful. Sometimes it's very easy to tell when data has been faked. There have been times when the same researcher has used exactly the same plot for completely different phenomena. They've just changed the labels. And then it becomes very interesting that you have exactly the same fluctuations in completely different situations. Amazing. But frequently there is a tremendous amount of concern as to whether or not you can trust, should this be a situation where Benford sets in? And so I was working with some people who had some questions about some protein databases where it was discovered that some of the values that were being inputted into the databases were fraudulent and were just made up. And the question was, could you have detected this earlier by doing some Benford tests? And of course, the problem is, well, do we expect the data to be Benford or not? And so, this is the $64,000 question. So well, I am glad that we made it through the rest of the talk with no additional technical failures. So thank you.
Thank you, Steve. We have time for some questions for our speaker, because I think our speaker has a few minutes before he has to rush off.
Are you still recording?
I can stop.
I don't want to say about how excited I am for my next meeting if it's being recorded.
Hang on.